Welcome to another episode of Bite Size Maths. In today's class, we'll be looking into the determinants of 3 by 3 matrices. And let's get started. So, in the previous class, we saw this matrix as an example, and we've calculated the minors of each element and the associated cofactor of each element. So, in case of 1, we had minor minus 16, cofactor minus 16, and so on and so forth. So we had all these minors and we calculated all these cofactors. So to find the determinant of a 3 by 3 matrix, you take any one row or column, any one row slash column, multiply the set elements with their cofactors and add them. So element into cofactor sigma. So let's see this in with our example case. So it will be 1 into minus 16 in our example case, 1 into minus 16 plus 0 into minus 10 plus 2 into plus minus 2 into 19. So this will be minus 16 plus 0 plus minus 38, which will give us minus 54. Now here's the fun bit. We did this with only our first row elements, but if you expand it along any row or any column and use the corresponding cofactors, you will still get the same answer. So let's see the results which I've already calculated beforehand so that I don't have to calculate it again. If we expand along row number 2, which is 3 minus 1 and 2, so let's just show the row number 2 elements here. Along row 2, we will get 3 into minus 10 plus minus 1 into 14 plus 2 into minus 5 minus 30 minus 14 minus 10 equals minus 54. Similarly, you do it for row 3 in a similar fashion. Here, row 3, you'll get minus 8 minus 40 minus 6 is equal to minus 54 again. So basically you can find out determinant from any row or any column as long as you take the correct corresponding cofactors. So let's continue. So now let's talk about properties of the determinant. Properties. Now, property number 1. If each element meant in a row or column is 0 in a matrix, then determinant will be 0. So what does it mean? So let's say our 3 by 3 matrix is 0, 0, 0, A1, A2, A3, B1, B2, B3. If you take the determinant of it, you will get 0 into 0 into 0, 0 into 0, 0 into 0. So you will get the end result as 0. Same case applies if the column, if any column was 0, because then you can expand along that column and you will get the end result as 0. So this is our first property. If any row or column has elements all equal to 0, then the determinant will automatically be 0. Property number 2. Interchanging two rows or columns changes the sign of the determinant. Changes the sign of det A. So what does it mean? So let's say we have a matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. We take the determinant of it. That will come as, let's say, we will represent with det A. Now, if we write a matrix in which elements are B1, B2, B3, A1, A2, A3, C1, C2, C3, and take determinant of this matrix, this will be equal to minus det A. This is what this property means. Interchanging two rows or two columns changes the sign of the determinant. Basically, over here, if you're, let's say, for example, your determinant was minus 54, like in our previous case, then interchanging any two rows or any two columns will give us 54 over here. Now, property number 3. If a row or column is multiplied by a number, let's say q for example, then det, determinant of A can be written as, okay, wait, let's make this less confusing. Instead of writing it this way, then the new determinant equals k times the, sorry, not k, because we chose the variable, because our number was q, will be q times original debt. So what does this mean? Simply put, let's say our matrix is, original matrix was a1, a2, a3, b1, b2, b3, c1, c2, c3. Let's say this was our original matrix, and our new matrix is a1, a2, a3, b1, b2, b3, and q times c1, q times c2, q times c3. Then if this has the determinant equal to, let's say, some value, like in the end, if we get the value of, let's say, 90, for example, I, I'm not calculating matrices right now, I'm just giving you a very rough example. Then in this case, the determinant of this matrix will be q times 90. Now if we apply this property again, the property number 3, and we do a scalar on a scalar multiple, so if we calculate debt ka, where k is a scalar, this will become k cubed debt determinant of a. Now if two rows or columns are identical, are identical, then determinant of a becomes 0. Basically it's a way of saying that if you know what, never mind that. And this is a special case of property number 6, which says if two rows are in fixed ratio to each other, ratio to each other, then det A is also equal to 0. So what does it mean? What do these two properties together mean? So let's say if the matrix is like this, a1, a2, A3, A1, A2, A3, and C1, C2, C3. The determinant of this matrix will be 0. Det A will be 0 for this matrix. In a similar way, A1, A2, A3 and KA1, KA2, KA3 and C1, C2, C3. The determinant of this matrix will also be 0. This is what these two properties are indicating. That in these two cases where two rows are identical or are in fixed ratio to each other, the determinant will be 0. Let's continue. Next property states if property number 7, if a matrix can be written as A1 plus x1, A2, A3, A2 plus x2, sorry wait, let's take the second row as B2s, not A2s, B2 plus x2, B2, B3, what am I doing? This should be B1, C1 plus x3, C2, C3. If our matrix can be written in this form, then our determinant of this matrix det A will be equal to determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3 plus the determinant of x1, x2, x3, A2, A3, B2, B3, C2, C3. So the sum of these two determinants will be equal to the determinant of the original matrix. This is property number 7. Now later on we will start seeing some row operations. So the next property is related to those, which states property number 8. If a row or column is multiplied by a number k and added to another row or column, determinant remains unchanged. So I do not want to extend this video any further. So we'll be covering the rest of the properties in part 2. We'll be continuing from property number 9 to property number 13.